Hello ladies and gentlemen, and welcome to our third video in Chapter 4. Today we're going to be talking about the idea of frictional forces and how they can influence an object's motion as it experiences other forces as well. So in this video, what we're going to be talking about is, first of all, what exactly is friction? Why does it happen? How does friction affect an object? What will it do to the object as it travels across a surface? What types of friction actually exist, and what is terminal velocity? So keep those four questions in mind as we move forward here. So first of all, what exactly is friction? Well, we've all experienced friction before in some way, shape, or form. And the general idea is, as an object moves, it encounters a natural resistance from the environment itself. For instance, if you slide a book across a table, it just doesn't keep moving and go from there. Instead, what happens is the book gradually will come to a stop, and if the table is long enough, it will actually come to a stop. In a similar way, you have, let's say you're swimming, it's rather than cold and dreary outside like it has been, instead let's say it's summer and you're swimming in your swimming pool. Well, you know that you can't just move through pretty easy. There's water you have to overcome. If you just push yourself forward and then just let yourself go, you don't just keep moving forward. Instead, the water is going to push you back and slow you down. That's friction, basically. And we're going to say that in each of those cases, the object involves a force that resists this motion and encounters that motion. And that force we're going to call a frictional force. So one of the key things with friction is it always acts opposite the motion of the object. Okay, this is a steadfast rule. It's there no matter what. When something's moving and there's friction, friction always acts opposite the direction it's moving. That's true no matter what. So for what we're going to be dealing a lot with, which is contact friction, when you have an object sliding across a surface, the force is always going to act parallel to the surface of contact, just in the opposite direction of its motion. You can see the diagram down there. We have a block. Let's say it's moving to the right. Well, the frictional force wants to prevent it from moving to the right, so it's going to slow it down the other way. So frictional force is going to act opposite the direction, so it would act to the left. And notice we just call it a FF for force of friction, and we say that it opposes any applied force. What we should say is it should say it opposes any motion. Okay, you can have forces acting in the same direction as the frictional force, that's fine. Just keep in mind that if the object all of a sudden starts moving the other way, friction changes direction. Alright, so there is a typo there. It doesn't oppose any applied force, it just opposes the motion. That's the key thing. It opposes the motion that's going, no matter what. Now, in terms of why we have friction, it's all based on what happens at a microscopic view. Okay, if you look at a surface at a very, very microscopic level, it's not smooth. Instead, it's rough. It has a bunch of irregularities. And what happens is when you have two surfaces come into contact, those irregularities can actually stick together. Think of it as like momentary molecular bonding. There's electrostatic forces between them. They're going to kind of grab onto each other and hold on, but then as it moves, they break apart as well. That's what causes friction. It's just molecules momentarily binding together and letting go. Think of it as like two mountain ranges moving across each other, or think of like a zipper. You know, there's these basically grabs on and lets go. So that's what causes friction in terms of just contact. Now, if you're moving through a fluid, like let's say you're swimming, what's happening there is you're running into all the particles in front of you. And it says there's friction moving through a fluid. It doesn't have to be a liquid. It could be a gas. Think of like sticking your hand out of the window while you're in a moving car. You know, your hand is pushed back because all those air particles are pushing on your hand and moving it backward. Okay, same thing moving through a swimming pool. You have the particles of water resisting your motion as you move forward through it. So friction is basically, it's just resistance. It's either resisting motion because you're dragging across a non-smooth surface, or it's friction because you're trying to plow through particles in front of you. Now, there are multiple types of friction we're going to talk about, and the two big ones we're going to look at are contact friction and fluid friction. Contact friction is friction that's encountered when you move across a surface, specifically a regular surface. Up to this point, we've only really talked about surfaces that are ideally smooth, meaning there's no friction. Well, of course, that's not really the case. Even ice has a level of friction to it. So that's going to be one of the main types we talk about moving forward is friction across a surface, contact friction. The other one, which we'll talk about briefly, and we won't really get into a lot with it, but it's something to talk about, is fluid friction. And that's when you move through some sort of what we call a viscous material, meaning there's particles there you have to move through. That can be air resistance, which we're going to talk about in this video. It could be moving through water, anything like that. There is a third type of friction that we will not be talking about, but I wanted to bring it up, and that is rolling friction. And that is the friction encountered by some sort of rolling object. And basically, by having some sort of rolling object there, you can minimize friction. That's the idea of ball bearings in a variety of machinery. It helps reduce the friction level. Alright, so let's focus on contact friction for now. And contact friction itself kind of branches off into two types. The first type is what's called static friction, which we'll refer to as Fs. Notice we use a lowercase f here. That just is a way to symbolize frictional force just by using lowercase f. So Fs is static friction. And the idea with static friction is it's a frictional force that exists between an object and a surface when the object is at rest. And the goal of static friction is basically just keep it there. It's not going to move. So what you have is static friction is the resistance felt by the object if it's tried to move, and you actually have to overcome this friction to start an object moving. Think of like trying to push a table, or think of like a school desk or something. Just try and push it. It's not going to move immediately. You have to overcome some amount first to get it moving. If you push on it really lightly, it doesn't move. That's because there's a frictional force there already that's preventing it from moving. That's the static friction. So static friction keeps it there. You have to overcome that to get it moving. And what happens is, in terms of static friction, it can actually vary. It's not one set amount and that's it. As the applied force increases, the static frictional force will increase as well. Okay, so it basically just keeps going up and up and up and up to match what's applied to it until you finally overcome it. And that upper limit is known as the maximum static frictional force. And once you get past that limit, it begins to move. So that means, if you can take a look here, we have three diagrams here. Notice in the first one we have a push force to the right, we have a frictional force to the left. Notice it is our Fs. And let's say, for instance, we push with 12 newtons of force. Well, in this case, that's no problem for the static friction. Static friction is going to push back with 12 newtons as well, and it stays at rest. There's no net force. 12 minus 12 is 0. No acceleration. In the second one, we now push with 20, and notice now we're actually going to match that with static friction, but now we're at the max. Okay, we're saying that it can match the push force up to 20, at which point it'll break. So when we get to 20, it's still net force is 0, so it'll still stay at rest. But now if we up that push force to 25, well, we're already maxed out with static friction. It's going to move because we now have a non-zero net force, and Newton's first and second laws take care of that. So that's the idea here. Static friction keeps an object at rest. It'll just oppose whatever force you apply to it. And the idea is it will do this up to a maximum point, in which case it'll break free and accelerate. Now, the second type of friction is what happens when it breaks free, and that's called kinetic friction. Another way we can talk about this is what we call sliding friction. Same idea. And the idea is this is the frictional force that exists between a surface and an object when the object is moving. So now we're actually sliding across the surface. And this frictional force, all this will do is reduce the net force on an object. Okay, it's not going to balance it out exactly. It may or may not. It depends on what force you're applying. But the idea is when you're moving, this frictional force is there, and it always acts opposite the direction of motion, so it's always going to reduce the net force. And if you don't have an applied force, well, what's going to happen then is you just have a force in the opposite direction of motion, and that means that the frictional force will be alone, so it will have a net force in that direction, so the object will decelerate, it'll slow down. And one key feature of kinetic friction is it's a lot less than the static frictional force. In some cases, it varies, so as we'll find out here shortly. But kinetic friction is less than static friction, meaning it's easier to push an object or keep an object moving when it's already moving than it is to get it moving from rest. So that's a neat feature of friction, just that once you're moving, it's fine. It's just it takes a little bit of effort to get it moving. And that's something we've all experienced, moving things around in our home or school or whatever. All right. And here's an example of how this works. Now, it should say kinetic friction, another error we have. For kinetic friction, the value doesn't really change. Whatever we figure out as the kinetic friction value, that's going to stay the same throughout. So if we start off with a kinetic friction of 8 newtons, it's probably going to keep that unless we do something to the object we'll talk about in a second. But notice here in the beginning, we have a sliding friction or a kinetic friction of 8 newtons. We're pushing with 8 newtons. Net force is 0. So it's going to be moving at a constant velocity. Okay, this is one of the classic forms here. Basically, we're giving it enough force to keep it moving. It's not going to speed up. It's not going to slow down. Now, if we increase our push to 10 newtons, now we're really overcoming the kinetic friction, and it's going to accelerate positively. So it's going to get faster. On the other hand, let's say we don't push as much. Now we're only pushing with 3 newtons. Well, the kinetic friction is still 8. We have a net force in the negative direction, opposite the direction of motion. So we'll accelerate, but it's going to slow down. Notice we have a negative sign there. So kinetic friction, it still opposes motion. Just now that it's moving, it can actually speed it up or slow it down. So something to keep in mind there. Okay, now, what affects frictional forces? Well, 2 things. First of all, how much contact there is between the 2 surfaces, meaning how much are they pressed together. And we know that, based on some of the things we've talked about in class, what's going to affect that directly is what's called the normal force. We've talked about the normal force before. Normal force is used with frictional force. They are proportional. The more the normal force is, the more the frictional force is. So that means if you really push down on an object, you're going to generate a lot more friction than if it's fairly light. That's why, for instance, if you're in the snow, they advise you to put bags of kitty litter in your trunk. That way it pushes down. Now that only works if it's rear-wheel drive. Otherwise, it's not going to do anything. Now, the other factor is material. The types of materials in contact will result in different frictional forces. And the reason is certain materials are more or less friendly to friction. And we have a value that kind of measures that, and we call that the coefficient of friction. It's a decimal, basically, that describes how much friction is present between 2 surfaces. It could be very large, it could be very small. And we symbolize that coefficient with a Greek letter, and it is the Greek letter mu. It looks kind of like a weird cursive U there. I'll show you a good way to remember that in class. It looks like a little kitty. We went over the symbol when we talked about micrometers way back in the beginning. And this coefficient is actually a ratio. It's the ratio of the frictional force to the normal force. So for kinetic friction, it's the kinetic frictional force over the normal force. For the static friction, or static coefficient of friction, it's the maximum static frictional force to the normal force. So actually the coefficient of static friction tells you what exactly is the most frictional force you can get out of it. Again, it could be less because it's static friction, but it's there. So, in terms of how they relate, you can see this table here. This is actually in the textbook, but we can look at that in class. Notice how the values aren't necessarily the same. They do vary based on what it is you're working with. And in some cases, the value can be high. In some cases, the value can be low. Steel on steel, static friction is 0.74, kinetic friction is 0.57. So 0.57 means that the kinetic frictional force is 57% of your normal force. Aluminum on steel is 0.61, 0.47. Notice how the static friction is always greater than the kinetic friction. Rubber on dry concrete. Notice we have static friction of 1. That means that whatever the normal force is, that's the maximum frictional force. And you can see there when we get to ice, notice how it gets really small. There's not a lot of friction there. So that's something we can use. Coefficient of friction gives us an idea about how frictiony the surface is, in the sense of is it rough or is it smooth. And with that in mind, we can actually calculate some of these frictional values here by using those 2 quantities. Coefficient of friction, normal force. This is our big equation. Ff equals mu Fn. Ff is our frictional force. It could be static or kinetic, depending on what it is we're trying to find. Mu is our coefficient of friction. Fn is our normal force. So if you have 2 of those things, you could find the third one. Alright, now, the other type of friction we have is air resistance, or fluid friction. We're going to talk about air resistance because it's something we run into a lot. And in class when we've talked about falling objects, we've always assumed there's no air resistance. And the reason is air resistance has a lot of detail with it, meaning it's not an easy thing to work with a problem. And the reason is that it's dependent on speed, but it actually changes as it goes. First of all, air resistance always opposes motion. So if something's falling, it acts upward, just like normal friction. And at low speeds, the air resistance is just proportional to the object's speed. So as you get faster, the air resistance increases. The problem is, when you get to a high speed, it actually changes. Now the air resistance is proportional to the square of the object's speed, so it gets even greater. So that is a key feature of air resistance, is that it's dependent on speed, but it's not uniform. It actually starts off linear, but then starts becoming quadratic. It actually gets greater and greater and greater. And that's why it's so complicated to work with, is it's not a nice, easy thing to deal with. It's not, linear, and it's just, oh, we can put that in and get it pretty quick. It changes as the speed changes, and that is a problem. So that's why we ignore it in a lot of cases. But the key thing is, as it falls through the air, an object will encounter an increasing amount of air resistance. So it'll get more and more and more. It's not constant. And what happens is, as it falls, it keeps growing and growing and growing until you reach what we call terminal velocity. At terminal velocity, that is actually the fastest speed with which something can fall. It won't go any faster than that. And this happens because you eventually reach a point where the weight of the object, what's pulling it downward, is opposed by the air resistance force that's pushing it upward. The net force is zero, therefore it no longer accelerates. So this is the fastest point at which an object can fall. If there was no air resistance, then first of all, if you went skydiving, you'd be an idiot because the parachute wouldn't work. There's no air to push up. And the other thing is that you would just keep getting faster and faster and faster. That doesn't happen. If you go skydiving, you actually kind of max out at a certain point and stop getting faster. So air resistance means that as we fall, air pushes up on us. We eventually reach a maximum value. If it equals our weight, we reach what we call terminal velocity. When we don't speed up any further, we'll still be falling, just we won't be speeding up. Alright, there was a lot of information in this video, but to hit some of the key points here. What is friction? Friction is basically just the force between an object and a surface that resists its motion. That's the key point there. Friction resists motion. How does friction affect an object? Its goal is to basically slow it down or keep it at rest. If the object is moving, friction acts opposite the motion, so it's going to act counter to any net force or any applied force you're putting on it. If it's at rest, it's just going to keep it sitting there basically until you overcome it. What types of friction are there? Contact friction, which is when you have an object on a surface. That can be static or kinetic. We talked about both of those. And we also have fluid friction, moving through any sort of fluid, liquid or gas. We also had rolling friction, but again, we're not going to focus a lot on that. And what is terminal velocity? Terminal velocity is the fastest speed you can attain while falling, and that occurs when the amount of air resistance you have equals the weight of whatever it is that's falling. Alright, we will be working a lot with this in class over the next week or two, and I will see you then.